Boa tarde a todos e todas. Sejam muito bem-vindas e bem-vindos. É com um misto, né, de sentimentos que estamos aqui agora, felizes por mais uma palestra, essa oportunidade, e tristes porque é a última palestra dessa edição 2020 do SIMMA, né, mas foi um evento muito bom desse ano, dessa forma diferente, acontecendo online, por conta da pandemia. Mas estamos aqui hoje para a palestra do Dr. James Anderson. James Anderson possui bacharelado em Psicologia Experimental e doutorado em Ciência da Computação. Foi pesquisador assistente em Engenharia e Ciências Aplicadas e Engenharia Eletrônica e pesquisador titular e professor de Ciência da Computação pela Universidade de Reading, no Reino Unido, onde se aposentou no início desse ano. E agora James Anderson mantém suas pesquisas de forma própria e é editor-chefe da revista eletrônica Transmathematics. Por fim, cabe dizer que ele é o criador dos números transreais que originaram a transmatemática. Eu gostaria de lembrar a todas e todos que podem e devem fazer perguntas e comentários no chat aí do YouTube. Nós estaremos atentos ao chat e, ao final, nós passaremos essas perguntas para o James Anderson. A gente lembra também que o link para a inscrição nessa palestra, que vai dar o certificado, o link está na descrição do vídeo no YouTube, também no site do SIMMA, e na descrição do vídeo também no YouTube tem um link para os slides que o James Anderson vai usar agora aqui na palestra. James, we thank you for your time, and now I give the floor to the speaker. Welcome, James.
Thank you very much. Well, thank you for inviting me, everyone. I'm going to talk about transmathematics. I will tell you why computer scientists like totality. So transmathematics is an effort to make mathematics total. There are three basic reasons. The first is that transarithmetic has no error states. And using an arithmetic with no error states has very many advantages. One of them is that you don't need to put any error handling circuitry in the computer chip. So the computer chip becomes smaller, cheaper, more reliable. The second advantage of working with a total system is that physics works at singularities. So if you're writing a computer program to control some physical system, it's very nice to know that all of the calculations you do will describe physically realistic systems. There will be no error states in the physics that you're modeling. And then we get deeply into computer science, talking about transcomputing, ways to make computers faster, safer, and more accurate. I'm not going to spend a lot of time on talking about the details of computer science. I'm going to tell you much more about the mathematics. At the end, I'll give a summary of what I've said. So, totality. Totality means that every function is a total function. One of the consequences of this is that it's not necessary to waste states in a computer. So hardware and software can be more efficient. Think about the memory in a computer. The memory is made up of words, the words are made up of bytes, the bytes are made up of bits. And every bit can be a 0 or a 1. There's no constraint on what those states can be. Every state is allowable. The memory is a total system. But when we use that memory in a computer program, we often overlay partial systems on top of it, such as arithmetic that cannot divide by 0. So now some of the states that we would like to use correspond to error states in the arithmetic. So either we must accept them as errors, or we must block those memory locations, not use them. So if we use a non-total system, a partial system, we are obliged, it's necessary that we accept error or we accept waste. So having a total system means it's not necessary to accept that waste. The huge advantage from the point of view of computer science is that every syntactically correct program is semantically correct. That means that if a program compiles, it will not crash for any logical reason. It might crash for a physical reason, but not a logical one. This means that if a program compiles, then there will be no runtime errors. The computer will continue running, it'll continue operating correctly forever until something stops, physically stops the machine. And that's very useful for implementing safety critical systems, such as those that control aeroplanes, nuclear power stations, and heart pacemakers. On this slide, I'm going to talk a little bit about the history of mathematics and transmathematics in particular. I will tell you a little bit about my educational experiences, and I'll talk a little bit about science policy. Once we've got this background material out of the way, we'll concentrate on the technical material. Let me tell you that I'm a psychologist, as Thiago said, and when I was at university, I was told a very interesting story about the origin of species, written by Charles Darwin. That was a paradigm shift in biology, but it was very controversial during Darwin's lifetime because there was no explanation of how genetics works. The experiments had been done on genetics. They were written up and recorded in the Vatican Library, and biologists quoted those experiments, but they never read the original papers. It took 50 years for Darwin's theories to be accepted. During that time, one biologist went to the Vatican, read the papers, and understood from experiments on peas how genetics works. And from that point on, biologists were persuaded by Darwin. So the advice I was given is never cite any paper you haven't read, and always read the originals of a paper. Don't rely on secondary sources. Now, I do use secondary sources. I'm a psychologist. When I need to learn about mathematics, I usually read a history book. The reason is that history books give a very simple explanation of the mathematics involved. They explain why the mathematics was important, and they tell you something about how it developed. Then I read textbooks. So that's how I approach science. I always go back to the primary sources. So, in 1997, I published a paper solving a problem in computer vision. So I was working on computer programs, working with ill-conditioned systems. The answers I got had no significant bits. The answers were completely rubbish. And I found a geometrical construction that would allow me to describe the geometry in rational numbers, which I could compute exactly on the computer without any further error beyond the error in the camera itself. And that construction was based on projective geometry and some ancient Greek mathematics. So I read the elements of mathematics, Euclid's elements, to learn that ancient Greek geometry. And the strange thing about it was when I took this ancient Greek description, it's written out in words, it describes a geometrical construction. When I wrote it as an equation, it had three unusual solutions. The solutions 1 over 0, minus 1 over 0, and 0 over 0. And these ancient Greek construction, these numbers, I knew they were numbers because they're solutions to an equation, corresponded to a construction in projective geometry. 1 over 0 was infinity in front of the camera, minus 1 over 0 was infinity behind the camera, and 0 over 0 was the projection point, essentially the center of the lens. So I had a geometrical description that told me what these three numbers were. I had an equation that told me how to construct the numbers. And historically, numbers are defined either by geometry or by equations. I had both. So that, and incidentally, it solved my problem in computer vision, which was very good. So I then spent 10 years thinking about these numbers, and there are many choices about how you can make an arithmetic. And I decided to make the smallest change to real arithmetic that would be consistent with calculus. In 2007, I published a machine proof of transreal arithmetic. And that proof was done with Norbert Volker and Andrew Adams. Norbert Volker is a very mathematical computer scientist, and I found it difficult to communicate with him. So Andrew worked as an intermediary, explaining the computational and mathematical issues to me. I'd produce the axiomatization, and then we'd produce the machine proof. The machine proof is the most detailed kind of proof is possible to have. So we were then happy that we had produced a system of axioms that prove transreal arithmetic total. They prove a consistent way of dividing by 0. In 2011, I was contacted by Walter Gomide. Walter is a philosopher in Brazil, and he was working on paraconsistent logics. Paraconsistent logics allow reasoning over inconsistencies. And one difficulty with establishing such a logic is how do you write down a consistent set of axioms that allow inconsistent reasoning? The methods that logicians use are very advanced. Essentially, they set up a meta-language which allows the inconsistency. But Walter had a different idea. And his idea was to take paraconsistent logic and arithmetize it, turn it into arithmetic, so that the logical operations and inductions became calculations in arithmetic. But he didn't use any ordinary arithmetic, he used transreal arithmetic. And the reason he chose transreal arithmetic is that he could use infinity to mean absolutely true, classically true. He could use minus infinity to mean false, classically false. He could use the intermediate values for degrees of belief in the truth and falsity. He could use 0 to mean equally true and false. And he could use the new number 0 over 0, which I call nullity, to mean neither true nor false. No other arithmetic gave Walter those choices that he needed. Now, I said that it's very difficult to axiomatize paraconsistent logics, but Walter noticed that there was a proof of the consistency of transreal arithmetic. So providing he correctly converts a paraconsistent logic into transreal arithmetic, there's no further need for a consistency proof. And from that point onward, I worked with Walter on a number of projects. And I still work with him today. Walter has been very important to the development of transmathematics. He travels around Brazil, he travels around the world, meeting people, talking to them, and he's introduced many people to transmathematics. About 10 people, more than 10 people, have published papers in Transmathematics. More than half of them are Brazilians who were introduced to the subject by Walter. So Brazil has more people publishing in Transmathematics than any other country in the world. One of the people Walter met was Tiago, who presented today's talk, and Tiago produced proofs of the consistency of transreal and transcomplex arithmetic. Those were constructive proofs, human proofs. And that gave us a second reason to understand that transreal arithmetic is consistent. Tiago introduced Roberto Cabrulsi, and Roberto set up the first international conference on transmathematics in Brazil, in Rio de Janeiro. We have a conference every 2 years. The next one is due in 2021. Because of COVID, it will probably be a video conference like this. I would very much like to come back to Brazil at some time with a Transmathematic conference. So thank you very much for inviting me to speak today. There is current research on foundations and applications of transmathematics. Chris Tucker is looking at applying it in electronics. A number of people are looking at different applications. Some of the people, Tiago and I, working on transmathematics, are looking at the foundations of transmathematics, trying to establish transmathematics as part of conventional mathematics. Another group of people, led by Jan Bergstra, are using conventional mathematics to analyze transmathematics, to exhibit the choices we've made. So they analyze transreal arithmetic, look at all the algebraic choices we made, show what the trade-offs are in transreal arithmetic compared to real arithmetic, compared to Meadows, compared to other methods of dividing by zero. And that's very useful because it explains to us the choices that can be made if you want to produce a total system. The huge advantage of having a total system, as I said, is that computer systems become more reliable, that they allow physical systems to be solved at singularities. There are several potential candidates for a total arithmetic. Transreal arithmetic is one of them, and it has been applied to a wider diversity of mathematics than any other approach to division by zero. Okay, so I'd like to start my discussion of the technicalities of transreal arithmetic with Sir Isaac Newton. You know him from his laws of motion, from his theory of gravitation. And Sir Isaac used the Arithmetica Universalis. The Arithmetica Universalis is a form of arithmetic. It's a particular set of algorithms for calculating arithmetic, and it has variables. It is essentially algebra, an arithmetical algebra. And Newton's Arithmetica Universalis predates real arithmetic. Newton died in the 18th century. Real arithmetic was first formalized in the 20th century, so clearly the Arithmetica Universalis came before real arithmetic. The Arithmetica Universalis is written in Latin. I read it in English translation. Some of Newton's lecture notes survive, in which he described the arithmetic. That was later published as a book called Arithmetica Universalis. I did not read the later book. I went right back to the primary source Newton's notes. So what I'm going to say about the Arithmetica Universalis is based on his lecture notes. I am perhaps one of his latest students. Now, when I read the Arithmetica Universalis, I got a surprise, and my surprise was that I already knew it. I was born in England. I went to a church school which taught things in a very traditional way, and they taught, in the mathematics classes, the Arithmetica Universalis. The school was very small. It was in a little village. When I went to school at age 4, there were about 9 people in the school. When I left at age 8, there were about 20. Much of the teaching was in small groups, but mathematics was in a big group. And I didn't realize that some of the material was intended for the older students, so I paid attention to it all. When I went to Scotland at the age of 8, I discovered that they did arithmetic differently. They were using the new mathematics. I struggled for a few years to catch up, went to secondary school, and secondary school taught algebra, and I'd suddenly discovered that I already knew the algebra because I'd learned the Arithmetica Universalis. I believe there are advantages in teaching children different things, that schools have different curricula, give people different experiences. This makes a country more resilient. Now, the mathematics that was taught in Scotland was the new mathematics. Let me tell you a little bit about the history of the new mathematics. So there was a space race between the Soviet Union and the United States of America, and the Soviet Union won. They put a satellite into orbit before the United States did. This was a huge shock to the United States of America, and so they conducted reviews to try and find out how it was that the Soviet Union had beaten them in this race, how it was that the Soviet Union had replaced them as the world's leading technological and scientific power. And they came to one leading conclusion, which was that they should teach mathematics better. And they changed the curriculum of mathematics in the United States to be based on set theory. And so the new mathematics was based on set theory. And then they sent teachers all across the world teaching the new mathematics to essentially every country they could. And they did this partly as an act of generosity to improve the teaching of mathematics, but partly as a cultural sort of way of expanding US culture. So they would contact foreign countries at government level, agree to teach the new mathematics, and then send teachers to teach it. The United Kingdom joined in this effort. The United Kingdom also adopted the new mathematics, and it also sent teachers largely to Africa, to parts of what had been the empire. So the teaching of mathematics for a number of years was an intensely political activity, driven by the need to establish technological and scientific dominance. And the message I take from that is that if a country is slow to adopt a new mathematics, it can lose its position as the leading technical and scientific country. And if it's fast, or if another country adopts a new science, it can overtake the current leaders. Right, that's enough of my political views on education and science. The Arithmetic Universalis does not outlaw division by zero. Division by zero is allowed. When I learnt the Arithmetica Universalis, no one told me that I shouldn't divide by zero. I think that if you tell children things at a young age, they simply accept them and aren't critical about it. But no one told me I shouldn't divide by 0 until I reached secondary school, by which time it was far too late. I already knew the arithmetic universalis. So the arithmetic universalis is not real arithmetic. It allows a number to have any factors. For example, we can write down 0 equals 0 times 1 times 2 and so on. Of course, we can write this down in real arithmetic too. 0 equals 0 times 1 times 2 is a theorem of both arithmetics. But in the arithmetic universalis, the right-hand side, 0, 1, 2, and so on, are factors, whereas modern integer factors are required to be smaller than the number they factorize. Rational arithmetic uses an integer factorization. So the arithmetic universalis makes it easy to divide by 0 because we can factorize 0, and rational arithmetic and real arithmetic make it hard to divide by 0 because we can't factorize 0. And that's one difference between the arithmetic universalis and real arithmetic. There are other differences. Newton gave a faulty proof that division by 0 is inconsistent. So Newton believed that division by 0 is inconsistent, but his proof was wrong. So what is Newton going to do about this? He has an arithmetic that allows division by 0. He believes division by 0 is inconsistent. What is he to do? He defines that x equals y if and only if x minus y equals 0. Of course, he didn't say it in that way, but the modern symbols fit conveniently on the slide. And that blocks the transreal numbers plus and minus infinity and nullity, because any strictly transreal number subtracted from itself is equal to nullity. If we read Newton's equal or equo as a modern equality and restrict division by 0 to transreal division by 0, then the arithmetic universalis is transreal arithmetic. If we make those changes, I have rediscovered the arithmetic universalis. And the consequence of that is that Newton's mechanics, his physics, work at singularities. We have to be careful what we mean by Newton's physics. He wrote a book, the Philosophia Principia Mathematica Neutron. Oh, I forget. I'll come to it. He wrote a book. It contained 3 volumes. The first was what we call mechanics. The third book is what we call celestial mechanics, and few people know what the second book was. The second book was fluid mechanics, and almost everything in that second book was wrong. One of the things that was right was the idea of Newtonian relativity. The idea that if you consider water flowing past a ship, the forces are the same whether the ship is in motion relative to the water or the water is in motion relative to the ship. And that one fact allowed the Navy to establish hydrological tanks to design better ships. And today we use that same principle of Newtonian relativity to build wind tunnels and design aircraft. So even though almost everything in the second book was wrong, it still had very useful consequences. So what do I mean about Newton's physics? I mean his laws of motion in the mechanics, and I mean the laws of gravitation in his celestial mechanics. Those 2 areas of physics work at singularities when you use the arithmetica universalis in the way that transreal arithmetic requires. Transreal numbers are a proper fraction of real numbers with a non-negative denominator and a numerator that is one of -1, 0, 1 whenever the denominator is 0. We define that minus infinity equals any negative number over 0, and this is equal to -1 over 0. Oops, -1 over 0 is the canonical form. Similarly, infinity equals k over 0 equals 1 over 0. 1 over 0 is canonical form. We've now described all negative numbers over 0, all positive numbers over 0. There's one number left, which is 0 over 0. So nullity equals 0 over 0 is a number. Each of these numbers is a fixed number. It's a definite number. If we're given a negative, an improper fraction with a negative denominator, then we turn the negative denominator positive, which we can do by subtraction, multiplication. If you're working in a computer system with a sign bit, then you can move the sign bit from the denominator to the numerator. Right, this is the definition of multiplication, how you multiply two fractions as to get a single fraction. And I'm sure you've learned this in primary or secondary school. At the point you learnt it, you had the option of making b and d 0. You might not have realized you had that option, but that option was there. Division a over b divided by c over d is a over b times, and we turn c over d upside down to produce d over c. This is the lexical reciprocal. We have to be careful. If c is negative, then d over c is an improper fraction, and we must move the sign to the numerator. If you're working with arithmetic, then you'll make that correction at the time you do the calculation. If you're working with algebra, you'll have to split the calculation into two paths, one assuming c non-negative, one assuming c negative. There is more work to do with transreal arithmetic, but it has the advantage that it always works, whereas real arithmetic fails on division by 0. To add to infinities, these are definitions. Infinity plus infinity equals 1 over 0 plus 1 over 0 equals 1 plus 1 over 0 equals 2 over 0. And now we do a factorization. 2 equals 1 times 2. That's allowed in rational arithmetic. But we also factorize 0. 0 times 2. That is not allowed in rational arithmetic, but it is allowed in the Arithmetica Universalis, and it is allowed in transreal arithmetic. We now cancel the 2's and produce 1 over 0 equals infinity. So as you might expect, infinity plus infinity equals infinity. We now know enough transreal arithmetic to understand Newton's faulty proof that division by 0 is inconsistent. So Newton believed that there were different infinities, such as 1 over 0 and 2 over 0. He believed that they had the same size when compared to real numbers, to finite numbers. Finite numbers are also real, but Newton didn't know that. But he believed that 2 over 0 is twice as big as 1 over 0. And the reason he believed that is he multiplied 2 over 0 by 0, cancelled the zeros to get the answer 2, took 1 over 0, multiplied it by 0, cancelled the zeros to get 1. So in Newton's eyes, 2 over 0 is twice as big as 1 over 0. There are a number of problems with that. The first problem is it contradicts the result in the Arithmetica Universalis, which Newton was using. And secondly, it requires that 0 divided by 0 equals 1. And we know that that produces inconsistent results in real arithmetic. Now, this proof Newton gave when he was a young man. He gave it before he wrote down the Arithmetica Universalis. He wrote it before he wrote down the fluxions, his calculus. There is a sense in which 0 divided by 0 equals 1 makes sense. And that is, if you think that 0 is an infinitesimal number, then it makes sense to cancel infinitesimal numbers. And as Newton was just about to invent calculus, that was a very good idea for him to have. So at the point Newton produced the Arithmetica Universalis, he believed falsely that he'd proved that division by 0 is inconsistent. And we do not know how he viewed 0. Was it an infinitesimal number? Was it the zero of real numbers that we use today? There is some doubt about what Newton's zero was. Infinity plus minus infinity equals 1 over 0 plus minus 1 over 0. Those have got a common denominator of 0 equals 1 minus 1 over 0 equals 0 over 0 equals nullity. The same with minus infinity plus infinity. An interesting case is this one. Minus infinity plus minus infinity equals minus 1 over 0 plus minus 1 over 0 equals minus 2 over 0, and we factorize it. Minus 2 factorizes as minus 1 times 2. We take the highest positive common factor, if any. We factorize 2, cancel the 2's, produce minus 1 over 0, and we get minus infinity. So using the arithmetic universalis, we get what you expect. Minus infinity plus minus infinity equals minus infinity. And this arithmetic has been around for 200–300 years. General addition is done this way. So if you're not adding two infinities, you're adding one infinity to some other number, or maybe you're adding two finite numbers, or you're adding a nullity on something, then you use this form. All of these forms allow the divisor to be 0. A over b minus c over d equals a over b plus minus c over d. The arithmetic of division by 0 is lexically identical to rational arithmetic. That means that every formula of rational arithmetic continues to hold, and now we have some new results involving division by 0. Transreal arithmetic is associative and commutative. Transreal arithmetic is only partially distributive. A times b plus c equals ab plus ac whenever a is not equal to plus or minus infinity. If a happens to be plus or minus infinity, it might still be distributive. It's still distributive when bc is greater than 0. In other words, when b and c have the same sign. And it's distributive when b plus c divided by 0 equals this new number nullity. Notice that the three numbers plus and minus infinity and nullity appear in the guarding clauses. Now, even though transreal arithmetic is only partially distributive, it's still total, because we can always calculate the left-hand side and we can always calculate the right-hand side. Real arithmetic checks for division by 0. If you find a division by 0, real arithmetic fails. Transreal arithmetic also checks for division by 0, but always succeeds. It's a total system. Newton used the Arithmetica Universalis. The Arithmetica Universalis can be restricted to real arithmetic, and that's what happened historically. People took Newton's Arithmetica Universalis, restricted it so it didn't have division by 0, and then it became real arithmetic. But there's something else you can do with the Arithmetica Universalis. You can extend it to have a modern equality and restrict division by 0 in the transreal way. And then the Arithmetica Universalis turns into transreal arithmetic. Modern equality is very powerful. It's sufficient to use a set equality. Oops. Okay. If we read Newton's 18th century physics as applying to real numbers, then they fail at singularities. If we read it as his physics as applying to transreal numbers, then they operate at singularities. Let's jump now to the 20th century, 21st century. Transreal analysis replaces the symbols minus infinity and infinity of real analysis with the transreal numbers minus infinity equals minus 1 over 0 and infinity equals 1 over 0. So now you can do calculus with limits of minus infinity and infinity. They're now numbers, so we can do arithmetic with them. The number nullity can also occur in transreal analysis. So now every real result of real analysis arises as the same real result of transreal analysis, but transreal analysis has some results that cannot be obtained by real analysis. Newton's laws of motion and gravity can be restated with transreal arithmetic and transreal analysis, hence trans-Newtonian physics operates at singularities. Once we have transreal arithmetic, we can calculate the topology using epsilon neighborhoods, and we discover that the real number line has its usual properties. There is a gap, and plus infinity is the biggest number. There's a gap, minus infinity is the smallest number. Other infinities, such as Cantor's transfinite numbers, are smaller than the greatest number, and they fall into the gap here. The reciprocals of those transfinite numbers fall below the rational numbers and above 0, and on the negative side too. The number nullity is unordered, and it lies off the transreal number line up here. So nullity isn't bigger than any real number, it isn't smaller than any real number, it isn't equal to any real number, it is equal to itself. Now, if you want to do physics with transreal numbers, this is the diagram you need to remember. It's possible for Newton's equations to describe nullity forces, and we can calculate with them. Those forces exist in the point at nullity. The point at nullity lies outside the space from minus infinity to plus infinity. So the projection of nullity into the extended real space is 0. So now we know that in the space we live in, which is described by real numbers, a nullity force behaves as a 0 force. We can still tell the difference between a 0 and a nullity force. If I had a glass of water at a temperature of 0 Celsius and I heat it up, the water temperature goes up. If I cool it down, the water temperature goes down. If my water was at a temperature of nullity, I add energy to it, it won't change its temperature. If I let it radiate energy, it won't radiate, it won't change its temperature. I doubt if we can have water at a temperature of nullity, but if we could do an experiment to show that that was the case and distinguish nullity from 0. 2's complement arithmetic is used in all computers. It's the way of doing binary arithmetic. The binary codes run 0, 1, 2, 3, 4, 5, 6, 7. Those are mapped on to integers. The code 0, 0, 0. Here I'm using a very short word length, just 3 bits, corresponds to 0. 0, 0, 1 corresponds to 1. 1, 1, 1 corresponds to -1. There is an operation called complementing, which converts one bit pattern into another, and it converts 0 into 0, 1 into -1, 2 into -2, 3 into -3, and -4 into -4. The most negative number stays negative. And that's a bug. That's not the way that integer arithmetic works. It is the way computers work. There's another problem. If I take 0 and add 1, I get 1. If I add 1, I get 2. If I add 1, I get 3. If I add 1, I get -4. These bugs of wraparound, and this is called the weird number, its absolute value is a negative number, are mandated in some computer languages. You're obliged to have these bugs in your programs. They have one more negative number than positive. There was a -4, there was no +4. And this has a consequence for people who build inertial navigation systems, that they go round in circles. They would like to correct that error, and they can do that with 2's complement arithmetic. We have the number 0, 1, 2, infinity. If we try and add, we can't get past infinity. We stop there. And now the complement of 1, 0, 0 is 1, 0, 0. The complement of nullity is nullity, which is true. If people who designed inertial navigation systems could use trans-2's complement chips, then the amount of circuitry they would need would drop by 80%. Their devices would be much smaller and power efficient. So there's a market there for someone to produce trans-2's complement in FPGAs, field programmable gate arrays. Floating point arithmetic, the x's mean that we can be +1, we can be 1 or 0. The green x is the sign bit, 0 means positive, 1 means negative. This is the exponent, this is the mantissa. With this configuration, all bits 1 in the exponent. If any of these red x's is a 0, it represents a nan. If they're all 0, it's an infinity. So I'll give you a moment to work out how many nans there are. It's 2 to a big power minus 2. It is, in fact, 9 quintillion, 7 quadrillion, 199 billion, quadrillion, 254 billion, 9 quintillion, 7 quadrillion, 199 trillion, 254 billion, 740,990. It's a huge number. It's one error state. It's 225,000 error states for every star in the Milky Way galaxy. Truly astronomical number. It's enough to double the accuracy of floating point arithmetic. Mathematicians spend a lot of time working out algorithms to calculate floating point arithmetic accurately. If you then execute it on a floating point chip, it throws away half the accuracy. If instead you used a transfloating point chip, then you would get double the accuracy, up to double the accuracy. So we replace the number -0 with nullity, replace the nans by mapping plus and minus infinity to the extremal bit pattern, and increment the exponent bias by 1. That doubles the range of real numbers represented by the floating point bits. And now transfloating point arithmetic is embedded in real arithmetic. We can get the transcomplex plane by rotating the real number line. Real angles turn up as arc length divided by radius. We're working in a wheel, which is a circle plus its center point. The center point has arc length 0 divided by radius 0. Where are the infinity angles? They're the windings on the circle. So if we want to take a rotation from A to B, we do it with the external line segment going from A externally to B. This ensures that we have some length of arc length, some non-zero arc length. We then, if we want to do a complete turn and plus the angle, we go around once, go around a second time, and stop at the end point. As we approach the vertex of the cone, we go round and round more times. At the apex, we go round infinity times. And the arithmetic of that agrees with the cone. We take the ancient construction of trigonometry. We can calculate the tangent, and we go from 0 exactly to plus infinity, 0 exactly to minus infinity. As we move over a period, we asymptote from minus infinity to plus infinity. And this arrangement, arriving at infinity exactly, is what the ancient construction of trigonometry gives you. So presumably the ancients knew this. Real arithmetic doesn't allow you to go exactly to infinity. After a gap, we have the infinities. They have angle nullity. We can calculate the angle nullity in a triangle with hypotenuse 0. It's 0 over 0 equals nullity. We have nullity over here. At one point, I wanted to calculate eigensystems. I used Jacobi's algorithm. It calculates cosines and sines. And it does it using the tangent and cotangent. It uses tangent and cotangent to avoid a division by 0. I read Jacobi's algorithm, and he does not do that. He uses only the tangent. Jacobi's algorithm has a division by 0 in it. We can represent that. We can implement it in transreal arithmetic, and then we end up with an algorithm that runs slightly faster than the modern one. I don't know if the modern algorithm is more accurate. So I've gone a bit slower than I intended to. Let me zoom on to exciting things. Sorry about this. You can read the slides. I'll get to Newton. This is important, and then I'll stop there. So, transcomplex arithmetic, we have a solid cylinder, infinity, and nullity. Polar multiplication and division are screws in this space, as usual. We can do addition, take a polar vector r theta, draw it as the unit vector 1 theta. So this red vector is some long vector, and we've drawn it as a unit vector. This yellow vector is some long vector, we've drawn it as a unit vector. Scale all the vectors below the maximum height by 1 over m. So we divide r by whatever height this yellow vector is at. And that makes the vector shorter. We then calculate the resultant as usual, and then renormalize the resultant into the disk at 1 theta. And that method of arithmetic replicates all of Newton's calculations with directed line segments. And so Newton's physics works with transcomplex numbers. If we multiply all of the disks by their height, we get this shape. If we project it onto a plane, we get the transcomplex plane as usual. If we sum vectors, the sum is non-associative unless we delay the renormalization. So if we put lots of vectors into the disk at infinity and then renormalize, then the sum is associative. So if you're doing physics, you must take a history over, you must take the history of all of the motions before you renormalize. Right, blah, blah. We made prototype computers. This one was made by Osvaldo Cadenas. Other people have been involved. Paul Johnson has designed one. Steve Leach has worked on software. The huge advantage of these, sorry I don't have time to explain the operation to you, is that the Fourier transform moves from time order n squared. It's not used in practice. The fast Fourier transform is time order n log n. The fast Fourier transform implemented on this hardware operates in time order n. So we used it for processing radar images. And the advantage is that you get a result every clock cycle. Okay, I'll leave it there and ask for questions.
James, we thank you for your time and your talk.
Sorry, I was so rushed.
No problem. Let me make some questions that people did on YouTube. I have here a question about quantum computing and transmathematics. I think you can see, but quantum computer is seen as an issue to some cryptography methods. How different is for cryptography the approach made possible by transmathematics?
Okay, there are two possible answers to this. One is the cryptographic methods people use are sometimes based on 2's complement arithmetic to cycle through permutations. That is a relatively slow operation on a von Neumann machine or a parallel von Neumann machine. On a transreal computer, sorry I didn't explain more details, you could perform very many operations per second. So a transreal computer might have 64,000 cores per chip. You might operate 1,000 or 10,000 times faster. So the practical answer is contemporary hardware could run faster on cryptographic problems. The transreal arithmetic has no special advantage for quantum computing. Quantum computing is extremely fast. We know of no method that would be faster. It's very difficult to build big quantum computers. if we get to a stage where we want to do computations that won't fit in a quantum computer, we could put quantum computers together into a slipstream, into a pipeline, and operate on them in the transreal way. That would allow you to calculate many programs per cycle of the quantum machine. So the answer is, in a practical sense, your calculations might run 1,000 or 10,000 times faster. In a mathematical sense, it makes no difference as far as I'm aware.
Good. Is Transmathematics, in some sense, a long time unseen by mathematicians? Application as projective geometry in computation. You talked about projective geometry in the beginning.
That's right. That's right. Yes, it is. Projective geometry has these arithmetical properties. I must be very clear. Mathematicians identify plus and minus infinity. They don't care what's in front of the camera and what's behind. Computer scientists do. They distinguish positive and negative infinity. We can also say that transreal arithmetic is a long missed result of Newton's Arithmetica Universalis. This was around for 200 or 300 years. The world decided to formalize the Arithmetica Universalis as real arithmetic. It could instead have formalized it as transreal arithmetic. Let me make the very, very important point that Newtonian physics works at singularities when you use the Arithmetica Universalis in the transreal way.
Good. I think you can read the question, please.
The answer is, I've been trying for a number of years.
Yes, excuse me. Could you read the question, please?
Yeah, read the question. Yeah. Is it possible to create a set theory based in transmathematics? How would we deal with the ZFC NBG axioms? Would they be modified? How would we discuss ordinals and cardinals in such a theory? Okay, I've tried for many years. I have a number of ideas. If we use a set theory with a universal set, then we can use that to represent the cardinality infinity. If we have an atom, we can use that to represent the cardinality of atoms. The empty set and atoms don't have elements, and there is a question, how do you distinguish the empty set from atoms? The way I distinguish them is that I give the empty set cardinality 0, and I give atoms the cardinality nullity. How does that affect ordinals? Well, if we want to express the transreals in a weak number system, such as ZFC, which doesn't have a universal set, then we can represent infinity as the set of all real numbers, and we can take nullity as an atom. ZF used to have atoms, we can put one back in, or we can take an object that has a structure different from the real numbers. Does it make a difference? Well, yes, it does. In ZFC, or ZF, there is no greatest number. The proof that there is no greatest ordinal fails with transreal arithmetic, because it's possible that the greatest ordinal is a transordinal, not an ordinal. So the usual objection to having a biggest ordinal fails. What am I going to do about this? I'm not sure. I'm very happy to collaborate with people on set theory. There is a straightforward answer. Yes, we can model transreal arithmetic in ZFC using the set of reals as infinity, some other object as nullity. But transreal arithmetic is beginning to present a bigger challenge to set theory. It provides a biggest ordinal, it provides a biggest cardinal, and the question is, how do we handle that? As soon as I've worked it out, I promise to tell you.
Thank you.
By your work in division by zero, may we have a different approach to the differentials and their relation with the hyperreal numbers. The work on analysis is largely done by Thiago. The transreal analysis contains real analysis. So just as transreal arithmetic contains real arithmetic, so transreal analysis contains real analysis, and so on. So we don't expect any changes to the fundamentals of analysis. The basic topological methods of analysis work equally for real systems and transreal. There are some changes to the definition, for example, of the derivative. The issue is that if you take infinity and approach it, then the height infinity minus n very finite number is a finite number. So instead, we take two limits approaching infinity. And that way, we don't get a failure of the definition of derivative. So yes, there are some changes you have to make to the definitions of, for example, the derivative. You have to change, for example, the complex integral so that it uses non-degenerate Cartesian coordinates. The complex numbers exist only in, transcomplex numbers exist in the polar form. So yes, the basic definitions do change. You have to change them in a way that contains the existing analysis, and then you get more results. You get results that you can't get by the normal analysis. The transreal analysis, transcomplex analysis are not total systems. It's still possible to have functions that have no transreal limits. If we were able to produce a total set theory that contained the transreal numbers, then we could have a set of all results, and that would totalize any mathematical statement about transreal arithmetic. Producing such a set theory is difficult. I've been trying for several years. I'm very happy to collaborate with other people. I will keep trying until either I succeed or I drop dead.
Okay. We have time to another question, Miguel. I think I can do other question here in the chat. Okay. And to avoid inconsistency, tau as division by 0, should we have another number system?
Yes, you should. And you should use a transreal number system. The issue is a very serious one. If you allow division by 0 and the result is any real number other than 0, then you get into contradictions. You can choose any number divided by 0 equals 0. That approach was taken by Patrick Supes in the 1950s. That system is consistent, but it's not consistent with analysis where a number 1 over x getting small approaches infinity. So if you want the real numbers to support division by 0 and produce a real number, you can do it consistently. You have to add some axioms. The issue is that the real number axiom, x times x to the minus 1 equals 1, only when x is not equal to 0. So it says that 0 doesn't have a multiplicative inverse. You cannot have a multiplicative inverse. You can define a reciprocal of 0, and you can make the reciprocal equal to 0. If you do that, you end up with all of the real numbers being used. The reciprocal of 0 is 0. It provides you with an algebra. It does not provide you with analysis. If you want to do analysis and do physics and things like that, then you need to provide at least a number plus infinity and minus infinity. And I gave you one more number, 0 over 0.
Good. We have some questions in English, but we have one in Portuguese. Let me translate. Is transreal space a connected space, like real numbers?
It has a finite number of discontinuities. So the real numbers are connected in exactly the normal way. There's a gap, and then plus infinity, a gap, and minus infinity, and a gap, and nullity. It's still a compact space, so everything you would expect to work with calculus, with integration, continues to work. So all of the theorems of real analysis generalize to transreal analysis. We believe that all of the theorems of complex analysis will generalize, but we haven't proved that yet. The sticking point is to produce a general version of the complex derivative.
Good. We have some more questions, but unfortunately our time is over. So okay. I thank you, James, for your time.
Thank you. May I just say, if people want to speak to me more, on the slides there's a link to a Skype meeting that takes place every Monday at 5:00 p.m. London time. You can come along and talk to me then.
Então, pessoal, como vocês ouviram aí no link dos slides, tem o contato de James Anson para quem quiser falar. E agora eu passo a palavra, então, para o Miguel, para o encerramento.
Obrigado, Thiago. Bom, a gente já, como o Thiago falou, a gente já passou um pouco do tempo. Então, eu só queria, em nome da comissão organizadora do SIMMA, do Departamento de Matemática do Instituto de Ciências Exatas, da UF de Volta Redonda, agradecer a todos os palestrantes, agradecer ao James Anderson, agradecer ao Thiago, que não é lá da UF, mas é a primeira vez que a gente tem um membro de fora da UF na comissão, ele é da UFRJ. Queria agradecer a SBN e a SBMAC, que ajudaram a gente de várias formas, a SBMAC, inclusive financeiramente. A gente tem feito esse evento já no 6º ano, com muita garra e pouco dinheiro, mas acho que tem sido muito bom, a gente tem aprimorando cada vez mais. Esse ano a gente fez dessa forma diferente, que com algumas desvantagens, a gente não teve a camisa, né, que a gente sempre tem, a gente não teve o café, o coffee break, mas a gente pôde, né, quebrar barreiras e trazer palestrantes até fora do Brasil, então eu acho que isso foi muito bom. E os vídeos agora estão gravados no canal do YouTube. Quem não curtiu ainda, quem não se inscreveu ainda no canal do YouTube do SIMMA, faça isso é bom pra gente. E lembrando que vamos ter mais um evento esse ano, que é o SESFEM. Então, procurem saber, em breve, acho que, se não me engano, acho que não tem data ainda, então também não vou falar besteira aqui. E agradecer principalmente a participação de todo mundo aí no chat do YouTube. Eu espero que todos tenham aproveitado. Então, com isso, eu encerro oficialmente o 6º simpósio de matemática da região sul-fluminense. Obrigado a todos.